accuracy. Ooh, thank you. That worked out. But yeah, being able to improve accuracy over time. And when we get to our case study, we'll show that, yeah, we definitely, we tune the model. Also, it's not only the additional data, but also cropping the images helped us out a lot, because we have kind of similar to this, we have a lot of right of way in the photo, but able to zoom in on the image and get a little bit close up and draw the bounding box there helped us out as well. So there's some kind of best practices or some gains there to be had.
Very cool.
Mm-hmm. All right. Any other questions as we continue on here? All right. Yeah.
I have a question. So the scores, the levels of trashiness, that can be interpreted as like a trash density model. Do you have hopes that the Google demo that we just saw could translate not just into a zip code aggregated thing, but more of a hyper local measure of this score in some way, either low, medium, high?
Yeah, so yes, I think for the general public, it is the kind of zip code base and the track base that they have. We did talk, and one thing we're working with them on is actually, yeah, how do we actually train it on a localized area and also for our right of way. And that's where I think Raina mentioned being able to customize it a little bit and allow for some photo uploads. And so the way I think initially right now anyway is to leverage, given that they've trained all of their street view imagery to identify trash, then basically apply it to, maybe there's room to do a batch upload, test it or train it, and then be able to test on those images, basically customize on a specific set of imagery. So that's something that we're working with them on, given that we'd also like to use it for OBTAs and other things that we're doing as a part of Clean California. So yes, that's something that we're planning for that platform.
Cool.
All right. Okay, so continuing onwards. So yeah, so I think in this case, yeah, they found that there were some false positives, a little bit as far as the actual segments, and this just showed basically what the actual trash count was. So in particular, some of the segments showed, this one looks like it stood out, segment 75. And then this gets us to the portion that we had for highways. So this is almost like a precursor in a way. I think we developed this in 2018, 2019. Big shout out to this because I believe it got started at Trash Datathon, the first one. So we started in a group, it evolved. I know Literati was there, and also input from Gary and others. So it kind of evolved from that. So this effort started in 2018. And then since then, we partnered with Google and started really kind of going down this path. So really exciting to see the evolution of this. So that said, so this is our automation study. And we started out in a similar effort. We took, the way we were doing it was we would have vehicles with a camera mount, GPS enabled. We'd collect thousands of images, which we could not even use because we're using the OBTA protocol, which means 2 people driving, 1 person with a clipboard, and everything was just super slow, right? Because you have to, score it manually. There's potentially human error. We have basically all the state right away, and also the ramps. Don't forget, we have to do the clover leaf, so we have to do 4 points basically. So it's very time consuming, and then also getting things into a map, whereas we had to digitize everything. So even with 2 full teams, like basically 2 cars driving around, I think it took us at least a couple of weeks just to do the Bay Area in District 4. So quite a lot to do. And then if we have to do these year round, I don't think, just the turnaround time and the resources required, it's just going to be, really super large. So I think that's where we started looking at this. And then it would help us, harness, because we already have the camera mount, why not just feed these photos into the model? So that's the use case. So this pilot was to show basically, could we replicate the human scoring? So the person actually in the vehicle scoring, could we actually replicate their score with AI? So that's what we were going for.
Walter,
yeah.
Just before you keep going, Professor Jin asked about what is segment ID?
Segment ID is, so basically the way when they're doing the city streets, like a city street grid, it would just be like a segment, kind of like we do on the state highway. It's just a way of identifying the roadway. You're going to take, say, 1 city block, 2 city blocks. For us, it's every half mile. So we just call that a half mile segment. And in that way, it's like on a map. That way we can, when we get the scores back, we can then just put it on a map and go, okay, this was high, low, that sort of thing. Thanks for monitoring the chat, by the way. Sorry, I didn't know.
Oh, yeah.
Yeah. Okay, great. Sounds good. Continuing onward. So we started out with, again, two different things that we were trying to do, very similar to the previous discussion. So there's first detection, and then there's actual trash rating or classification. So two things, which again, we basically split this into two parts, two models. And actually the demo that the hands-on part of it will actually talk, this will do these two things in different places of the code. But this is how, as far as object detection, litter detection is one way of going about it, commonly accepted. So this is a very high level overview. We're going to feed the images off our vehicles, right? It's pounded. We're going to do some automation. This is a very high level. So this has actually two models in it. We're using an ensemble because it's using weaker models to combine to a better score. And in output comes these ratings where, a low is very low detected versus high has many more items. And then embedded is actual where we say, okay, above a certain threshold, it's going to be, low, medium, or high. So this is actually the actual workflow. So we would actually feed the images into the actual detection. So the first thing is it just does the detection, right? Figure out what the objects are. We did not try to say what type of trash. We just wanted to know that there was trash. So we did a lot of human scoring, labeling to get the training data. And then from there, the second one was more conventional where we just fed it the actual scores, like this is how many pieces of trash, and then it will actually analyze and then give us a score back. So this is the computer vision part of it. And then this is the actual tabular part. So it's kind of putting, again, that taxonomy in the morning. This is computer vision, and then this is machine learning. So you kind of get, two use cases of machine learning, slightly different algorithms, and then it comes together to create one workflow. But this TensorFlow actually does, we don't actually quite get to the rating, but what it can do, it gives you a classification back for the type of object. But behind the scenes, this is typically the way you have to first find it, then classify it. So and that was the overall workflow. Yes, go ahead.
So one of the challenges that you often come upon when it comes to detecting trash in images is that trash is very much about like positionality. That is, if you have something that is a car on the street, that's where the car should be. It's moving down the street and it's in the image. That's not trash. But if a car is if it's in the greenery there, whether it's pieces of a car, a tire, car parts, bicycles, other vehicles, which are the things that may be discarded and left on the side of the road and could be considered trash, particularly like tires. Tires on a car, good. Tires in the side area, bad. How do you accommodate the detection of things in terms of how they are positioned?
Sure, excellent point. And I know the way we probably did it was just through a lot of labeling. So it was very time intensive. I think we took something like almost 10,000 images out of District 4, and then we actually did a ton of labeling. I think like I mentioned before, cutting it up so that we get it down to just that object. And so, we don't feed it in like this, we would actually get a close up. And then from there, I think that helped with some of the false negatives. And then also for us, because we're dealing with water quality, so our objects were always smaller. We weren't looking for the bigger, bulkier items. Though I think where we run into the problem, like you saw in the street sweeper, is the cigarette versus the lane line, because you can't wear a rock, right? You get into those places. And then I think that's where the human intervention, and then we only got, we were able to, I guess, spoiler, but we replicated the human score, but there's always that 20–30% where you're mislabeling. And then also the rule of thumb is just human eye, right? It's like these objects out here, it's like, is it really trash or is it a rock? But it would just be a human assessor too, right? If you're sitting in a vehicle 60 miles an hour. So those are some of the ways, I think, just the type of object, and then also a lot of labeling, and just the quantity of training data helped us keep that low. However, we can't catch everything. So we're always going to QA. And even I think in the future, if we want to roll this out, we presented this to Region 2, the Google demo. So if they let us use this, then, constantly having that human interaction of assessing the results, get back. And then, in a way, it's also better than a human score because we still have the photo, which is the proof, right? We can go back and say, hey, does this look right or not? And then maybe, err on the conservative side of, if it looks moderate, let's keep it moderate and not try to move it one way or the other. So kind of a couple safeguards there, but yeah, there's going to be, literally this is finding a needle in a haystack, right? You're trying to find these little specks and then try to discern are they correct or not. So.
Thank you.
Yeah, no problem. Okay, continuing onwards. So yeah, this is kind of how it worked, right? So we would feed it an image, and there's a whole lot, and I think we initially started out with this and we realized this did not work that well, the entire image. So we basically cut it up, and so we actually, process the images and we actually set it in tiles, and this worked out a lot better. And then this is the kind of the initial, this is the detection of, if you give it one image and it's split this way in the tiles, and then it's actually going to detect. So in the overall image, it's going to get 12 items, and then area of the image covered. So this is in a way like if it's got a big trash pile, but in this case, these are very small objects, right? So they're going to take up a very small total area, right? Versus, you could kind of get a sense of like density or just how much, right? One pile versus, maybe a dozen little things. Proximity score is like clustering, so these are pretty spread out. So it's not like, again, it's that whole density and piles of trash problem, right? So when we think about city streets versus things that are a bit more spread out, it gives us a sense of that. And then yeah, it talks about specific clusters. So this is probably a function of these other two. Just trying to get a sense of is this a big cluster or is it just a number of spread out type of objects. So this is our approach, and then again, it seemed to work pretty well. And this was iterated as well, right? We first started out with this, didn't work too well. We got to, okay, we're gonna cut it up, and then actually, how do we arrive and how do we calculate this? So this is done iteratively. And then continuing onward. So yeah, this is kind of what we saw where we started out with the full res, and then we would just develop these models in iterations, and then we plotted the performance of several of them. So through each iteration, we discovered how we could make it better. Because at the beginning, it was not doing that well. But then again, we found what is the right size for them, being able to parcel it, cut the tiles down, and then over time, again, we were iterating. So it's not a one model size fits all, right? You have to think about the image processing you might have to do. It might be lighting, might be positioning, might be more data, might be labeling, might be cutting up these images. There's a number of ways to do this, the processing, and then iterating and developing this model over time. This could probably be done. I mean, we did all this with coding, obviously, but on a consumer-facing app, probably just very quick wins would be trying to cut up the image, just doing actual processing of the imagery. And then let the models do the rest. And the tuning, again, you might be limited with a UI, but if you're able to have access to the developer, that's typically how you'd be able to iterate across these models. So continuing onwards. So this is again.
Walter, just really quickly, were you scaling things down or cropping things and kind of segmenting imagery to improve the training performance, or is it about more that it was actually not working? That is, was it a slower performance, or was it just choking on the larger imagery?
No, it was just accuracy. So yeah, we would just go through. Yeah, we were finding that the scores, well, you could kind of see, right? Some of these were not that performant, but I think we experimented with different ways of tiling the imagery, and then that worked a lot better. We partnered with one of our consultants on it, and yeah, I don't think they mentioned it slowing down. They'll probably within reason, right? You feed this thing like 5 megabyte photos, it's just going to take a ton of time, and it's probably not. And also, there's kind of an optimum between, when you feed it an image that's like huge, it actually doesn't use like 90% of it, so it's actually a waste of resources too. If you feed this whole thing, it's only targeting a couple of things, so it's I guess you kind of get it as a side effect. You're not sweeping this big canvas. You're only going to target, and then also by way of that, you're being more accurate, if that makes sense. Mm-hmm. But yeah, there were definitely some best practices that we picked up along the way for that. So, all right, continuing onwards here. And yeah, feel free to chime in with any questions. Let me check the chat if anybody is, yeah, okay. So continuing onwards here, I'm gonna go to, give me a second here, try to monitor some work stuff here. So continue onwards. So yeah, this is just in this case, this was concluded as a moderate because it's got 12 pieces, but it didn't have like big piles or big, a huge area of trash. So in this case, this kind of, that's an example of the classification or rating that we did. A little bit more on technical details if you really want to know how we came across. So this is the second part of it, whereas this is the first part, the actual computer vision part. This is where we actually arrive at the actual rating. And the way we do that is with the decision tree, right? Which you talked about in the morning. So it's a random forest. So basically, it's using a bunch of weak filters. It's basically checking row by row of data, and then it's going to return a score. And so very high level, but it makes a bunch of passes using weaker classifiers, and then it averages the score. So it's going to focus on, maybe a particular column of data, and then it's going to make a forecasted prediction for each row of data, right? So it's going to actually check across this way and then actually make the prediction. And then, you're going to give it a target. You're going to say, okay, predict, focus it on OBTA ratings. And then some models or some software, you can actually see the way decision trees, they arrive, and it actually looks like that. There's like a series of decisions, and it's actually doing splits, and then it's going to do it a number of times across different features of the data, and then it's going to bring these together and arrive at a score. And also, decision trees or random forest is really good too for finding feature importance, so you can find out which are the biggest influencers of your score. A common tool in Python would be scikit-learn. There's ones in R. I mean, random forest is pretty common. There used to be also, and there still is, Microsoft as a tool, which actually enables you to do like these little workflows without having to do, the name of it, it's called it's something workbench. But yeah, they have like a workbench tool where you can actually design these workflows without having to code at all. So that said,
is it imagined that the 4 images that you have represented on that make up like a single segment, and you're trying to take those 4 images and decide if that segment is to be rated low, medium, high?
That is correct. So basically, yeah, so these would be like 4 images, and these are, say, half-mile segments, and then it's actually going to make a prediction per half-mile segment. Does that answer it? Kind of like, and then the next one would be half-mile, half-mile, half-mile.
Yeah, I guess so. So each one is a half-mile.
Yeah, that's correct. And it may be that spaced together more closely. I know we take it at tenths, but I think for the official rating, the OBTA protocol, I think we agreed on a half-mile.
Okay.
Yeah, and then this would get mapped. So the part of it too is that once we get it to this score and we know for a half-mile, it makes the mapping super easy, because then we have the post-mile. So what you don't see here is we have the post-mile in the state highway system. So we have the location, the score, and basically the data to arrive at that score. And we basically just, we have the begin and end post-mile, just drop this in the GIS. And then so like for our reporting, right? Yeah, exactly, right? It's like the workflow. It's like a beautiful thing, right? We go to this workflow, we just drive along, we collect this imagery, right? And we go, okay, snap, every half-mile. And then we send this thing into the model, right? And it does the scoring and all that good stuff. And then once we're done, we get this output, right? Because the model just spits this out. We have the post miles along with it, and then off the GIS it goes. And then we report from there. So
that's great.
So continuing onward. So so that would be the workflow. We drive, collect the imagery, let the machinery do its work, get the scores back in the basically a tabular format, and then off into mapping and reporting. So this is a little bit more around precision and recall, but basically ways to proximity score. I'm going to go back. So proximity score, I'm going to take the question in the chat. So proximity score is when we talk about, this is the number of objects. And then the area, so it's basically the area of the image. Is it a big pile or is it a bunch of small items? And a proximity score is basically how close are the items to each other. In this case, they're pretty spread out. Whereas if they're all in one big cluster, this score would go up. and then it will probably drive to, you know, in this case, it treated all these as just one, but, you know, proximity is just trying to show how close, it's basically like clustering, if that makes sense. I guess, did that answer the question in the chat?
Looks like it.
All right, sounds good. All right, continuing onwards here. Continuing onwards here. So precision recall. So basically, precision is just how close are they getting to the actual objects, but then recall is where, you know, you're actually getting, you know, because it's just you're picking up how many items can you pick up, right? And then recall is actually how well are you matching. So in this case, if you're looking at the red boxes in this case, you're finding, so the red, remember, are the predictions, right? So you're going to find that this was, you know, it actually picked up on, you know, it got, you know, the items, right? But then, you know, you're actually trying to match it up to what did it actually, because this is a human labeling. So in this case, you actually had one mislabeled. So you're kind of going, recall is obviously the more important metric because precision is just saying, can you pick everything up? But then the recall is where you're actually lining up, you know, is it actually matching up with the human scoring, which is what we want. And then these are the metrics that we got. So again, recall being pretty important. So this is kind of how we can think of it as arriving at about 70%. And again, we're going to QA and verify with the human score, with the human eye, right, when we actually get done. And then again, some other examples of, again, some of how small these objects can get. This is what they call a confusion matrix, but basically across, you know, we don't want stuff on the boundaries where, or on the outsides where these are basically false positives and negatives. And what we want to see is that things that we actually label, the actual trash is, you know, what we have in the human or labeling, and it predicted by the model we want to match. So in this case, we're getting a pretty good number. And then again, this helps us assess how many false positives, false negatives are we getting versus actual true matches. So that this is what we're looking for. And in this case, this is kind of the final, you know, the final arrival that we had. And this is just an example. So say these are the every half mile segments. So in this case, what did the human assessor do? And then what did the model do? And we arrived in general in this pilot of about 70%. So, you know, and this kind of lines up with the Basman studies of about, you know, 80-ish% for human assessors, two different human assessors. So I think we just wanted to assess, you know, the feasibility and also the accuracy of the models. And I think we did a fairly good job in both the methodology and in also the results that we got.
It would be interesting, another measure I think that's really valuable, and this speaks to kind of Bob's emphasis on repeatability and standards and exchange. It's just if you were to, you know, I wonder if anyone's considered this, where you take images down that roadway, you run it through this, and you get your scores. You take the same roadway, but you maybe drive the opposite direction, but you're still photographing the same space. So you're capturing the very same landscape, but from a slightly different angle. So it's not the same image. And to see if the same model renders the same result. In other words, ideally, you would have a model rating of low for that particular area from whether you're driving forward or backward, right?
Right.
Yeah. And so because it may be actually more important to know, is the model consistent with its own rating than even if it's consistent with a given human assessor, because there's already variability, you know, among assessors.
Sure. It could also be the device, right? Maybe it's like a forward backward camera, or, you know.
Yeah, you could do it that way too. Yeah, I'm just saying, like, not reusing the same images, because you're going to get the same result from the same image, but you have slight variability of the imagery, but on the same landscape, so that you know how much it comes up with the same score for the same landscape.
Mm-hmm. Yeah, that's a really good point. Yep. Sounds good. Yeah, thanks for that. Yeah, so this is, you know, we got about 70%, you know, Basman in their study got about 80% for human assessors. you know, again, academic studies, they're showing that, you know, about more or less in line with what they're finding. And this was using, you know, UAV or drones. And then again, also to show sweepers, they also got, you know, kind of comparable if, you know, they got about 70% of, I believe, on their recall, or this is ours, but then also this is kind of what they got, right? So in this case, they got about 60 on the recall. Precision, they're a little bit better, but again, we talked about recalls where you actually have to match. So that's the more important metric. Next up, this is for us, but basically, how can we develop this? I think we're fulfilling this with the Google pilot. So I think we set this up as, hey, it would be nice, but we're actually getting into that. So this is super exciting. Last one before we move on, I promise we'll get to coding today. So we're gonna do one more and then feel free to reach out. So this was done with UC Irvine. And so this was their driving. They actually went out, and this is Fusco Engineering. So you can actually see they did this on a city street, and you'll see the camera here, similar to ours. And they had a driving vehicle, and they actually did streets. And I think they partnered with UC Irvine students. So in this case, they wanted to do, again, try to supplement or, you know, assist with the online visual assessments. And then these are the different methodologies that you have, right? The actual qualitative, you know, both pros and cons, things like that. You know, and in this case, this was, you know, not necessarily driving like we do, but more the walking methodology, like we saw in the, you know, in that last slide of a human assessor. I think this is video, and it doesn't render here, but they did have a video where they're actually driving along and they actually pick it up. So bummed out about that. But this is kind of what the output, you know, again, it's a mounted camera, and they're able to detect very similar in this fashion. I think they did a little bit more with trying to bucket and trying to quantify and also classify, which we'll see in these slides. So in this case, a very similar, you know, ways of clustering. What is the overall area that the image covers? So in this case, a very similar. We didn't compare notes. This is just, you know, everybody's kind of doing a very similar way, right? That what is the actual, you know, the amount of trash covering this photo? In this case, these were a little bit lower. You can see the little green dots. However, here they start to cover a little bit more in the image, and same thing here. So you get a general sense, you know, maybe more compensated for the angles, right? You can actually see that, oh, these piles of trash are actually taking up larger, therefore there's probably higher quantities. In this case, yeah, you can see that, and in a way, it's a different way of doing it. They're doing it more by area, that you could also do a count. You know, you're just using different metrics, but you're going about it the same way. In this case, and this is what they mean by segment ID in a way, right? These are the different segments that they did. And then again, they start to line up with scores. And this is the way our mapping looks as well. We basically cut up half-mile segments, we get a score, and we line up along a highway, and then we're going to get this and be able to show what the results of our heat maps, right? And in the future, when the Google demo and the Street View platform comes online, or the Litter Insights, they're going to do it by track and not necessarily by roadway. But again, very similar workflow of, you know, doing the automation and then, you know, mapping for visualization and reporting. In this case, they actually did a, you know, they actually took quite a large swath. So they did, you know, they cut up different areas. The lines here are the different segments that they did. In this case, I think this is just a county map of kind of the areas that they're looking to do. You know, a little bit more calibration, going out there, running their models and driving along. And in this case, I think they were also matching. So I think they ended up with, so they actually did, you know, pre-calibration of 50%, and they increased it. So calibration, tuning, training, more data, it kind of almost always leads to hopefully better accuracy. They also did another methodology. So this is very similar to you know, trying to equivalent the actual observation or scoring to trash loading. So this is their way of doing it, and they're kind of verifying and checking with that methodology. Pros and cons of the process, and then I think that was the bulk of it. Yeah, so I think the key takeaways here were, you know, really arriving at, you know, doing this pilot, getting through city streets, and then also, you know, things like this, where they're actually able to drive along and, you know, successfully detect the items, and then come arrive at trash levels based on the area of the image covered. So there you go. So a couple of different ways, right? Street sweeping, driving, city streets, and highways. different ways to apply computer vision to to the trash space. All right. Any questions before we get to the group exercise, the actual hands-on now?
Do you have any insights into why they angled things straight at 90 degrees out instead of the angle that you took, which was like a 45?
That is
it just means to me that they have a lot more images maybe over a narrower space than if you shot at a 45.
That's a really good question. I know for us, you tend to get a bigger swath, and also because I think of video, maybe the way the lens works. I know for us, we were trying to maximize because everything is just like, we're trying to take for a half mile. So I think for us, that was why because otherwise we're not getting enough of the image versus maybe I think you cover enough with the city street, right? Because you're also driving at a slow enough speed. So there may be a number of ways, but that's a really good point. I never really thought about, I know that we always did it kind of at a 45, but what would be the advantage or not? Maybe I think this way, obviously you probably, if you're kind of straight on a 90, you'd get a better shot, right? You're not getting the skewed angle on it. So you're kind of trading off, right? You're getting a better straight shot at it versus, you're covering more area. So, but yeah, it's a good consideration. All right, so hearing none, I'm going to switch over to the hands-on demo part of the, I'm going to can you all still see the browser?
Not yet.
Maybe I got to share the screen then. Okay. So I'm going to go back to the slide. Sorry, let me get to these slides here. You all should be able to see.
Now
Here we go. You guys see the slides?
Yep.
Okay, perfect. So gonna go back to the slides here. We got a couple of projects for you all. And I think given that we have limited time, but here's some of the projects that we have. And I just want to point out these are more like hands-on coding tools, many of which are used. And I think this is more for if you actually want to get hands-on and you actually want to edit. Though, like I mentioned this morning, is that Google Cloud, they have the Vision API, what they call the Vision API, but they have a number of, they have a service where it's more user-facing and you can do uploads and things like that. And then also Microsoft, like I mentioned, right? They have their cognitive services, and then they also have computer vision. So these are more consumer-facing, and then Amazon has recognition. So in this case, again, they're going to do a variety. They're going to have video, and they're going to have imagery. And then again, these are more UI-based. And I would say for those looking to get started, we're seeing more and more of these like through Microsoft, right? Like, at the state, we have Microsoft Teams and Power BI and other things coming up online. And then also we're getting more and more service contracts for, AWS and other places. So I think more and more these are getting baked into the cloud platform. So I think that goes a part of these efforts. So if you're in your organization, probably think about like, what's the organization's approach to cloud, and is there capacity to bring on some of these technologies? Because a lot of times they get bundled, and that's the way we're kind of going about it. Is we are currently, obviously with Google, right? But we've also been talking to AWS for data warehousing, and what are some tools that come with it, or Esri. Esri has the Esri Insights, so you can actually do spatial analytics and actually it actually runs machine learning in the background. So that's another way to access these tools. So I would say, any of the big tech companies, and then also Esri again is starting to come up with their offerings. So I just want to mention that. So as far as the open source, if you want to kind of roll your own, these are different ways to go about it. These are in general categories. So data analysis or data processing, there's some tools in R and Python. These two are the leaders. Data visualization, these are just for plotting, though there's also some coding tools for mapping. You can actually do a hybrid where You can generate code maps on the fly using code. So Python and RSM libraries for that. Machine learning, I talked about scikit-learn. So decision trees, random forests go there. R also has a machine learning, and then we get the computer vision, which is the demo today. And then here is the first of, the example. And also I want to point out, Google has a machine learning crash course that I think I may have mentioned last or earlier this year when we did this. So those that actually want to like start from scratch or learn more, they have a complete crash course for free, and they actually specialize in TensorFlow. So that would be the tutorial that we're looking at today. It's free. They have a series of different videos on different topics. So there we go. So that you're going to get it in bite-sized chunks. Let me turn off the dark mode here. So there you go. So, and they have a number of different techniques, right? So this is the auto-generative, probably the cutting edge stuff, recommendation engines, clustering, data prep. This is a big one. This is data processing or preparing data, learning how to ask a question for data science. So I'm going to put this in the chat as well. And then also want to point out one more, Kaggle has excellent, we actually use this at work for, I actually taught a Python workshop at work using Kaggle. And in this case, they actually have a series of courses where, again, you can start from scratch. They provide you the workspace, the Jupyter notebook, everything, just kind of like we're going to do today. So it lowers the barrier to entry. You can start at the very beginning in Python because that's, that's kind of what they're geared towards. And they have, if you go into each one of these, they basically have a series of modules and literally starting from scratch. And then you can save your work here with a Kaggle account. It's a free service. And then from there, you can actually do other things within Kaggle, like you can actually explore their data sets they have. They have some data competitions. And then again, you can save all your work under code. So I'm gonna also put this in the chat. And of note is that they cover all the major topics. So they cover Python. These things are for data processing called, there's a framework called Pandas, how to do some visualization, to, charting your results. So when we see those graphs with like accuracy, all that stuff, you can do it in Python, or TensorFlow has some tools as well. They teach you a little bit about databases if you need it. There is one on computer vision. So we do not have all that time today, or in this workshop. However, you can go through these and learn a lot more about all the techniques, about the nitty gritty from the ground up again. And they have both a lecture notebook and also hands-on exercises on how to work on these. And I think the homework on this is actually doing an actual case study where you actually work on one of their Kaggle dataset competitions. So pretty interesting stuff. And then continuing onwards, geospatial, like I mentioned, you can actually generate maps of code, if you'd like, but of course there's Esri and other things. And then a lot more about machine learning. So you can do, intro, intermediate, feature engineering, actually how to create your features from data, intro to data, they keep going on and on and on. Like, so you can pick and choose at your own leisure, but there are plenty of resources, but I found this super useful because they are free and you can save your work. You don't have to worry about installing Python, you don't have to worry about installing Jupyter. It's just there for use, and best yet, you can save your work. And so, for example, this is my personal account, but you can see that you can actually go to your work and it will just save your stuff. So these are some of the workshops I taught for CalTrans, and we did Python training. And then in this case, I just actually cloned some of the notebooks to start teaching, and then you can save your work. Any questions? Yeah, go ahead.
Yeah, this is all so valuable and so great. I mean, just the Kaggle resources alone, let alone all the other stuff you talked about, but just the idea that that the people in this work group that right now could incentivize their peers to share. They could share these resources with their peers so that everyone builds a certain level, kind of bottom level of literacy with these new concepts of artificial intelligence and these different types of tools to work with those concepts. I think it's really, it is very important that I think we all share certain nomenclature in common and concepts, because otherwise you could go down you could be in a position of decision making where you go down a certain road that doesn't lead you to where you want to go. One thing I want to point out, just in along those different pilot studies, that I find really intriguing, is sometimes the devil's in the details, which is not to say anything is wrong with anything that you presented, but some of the pilots were measuring, just when you get down to what was being measured in the images, sometimes it's like items per area, and other times it might be like pixels, or overall percentage of the area, and those aren't necessarily the same thing. And so thinking about how those measurements need to align with the monitoring questions that you might be asking of this monitoring, I think it's just a reminder, first of all, that it's really important to make sure that if you are starting this kind of pilot, that you're really careful about what you're trying to find, what you're trying to locate, in terms, are you locating pixels? Are you counting items? Because you might find really small items that have a relatively small contribution to the overall trash load, but maybe you are very interested in those small items because you're really interested in cigarette butts, or you're really interested in things that are liable to become microplastics very quickly. So, it really depends on what you're aiming for. That's one thing. Another is that, and I think this is really, really important, the vast amount of data, Walter, that CalTrans has collected, that all these different pilots are collecting, they are, first of all, those raw images, which, and then the images that are annotated or not annotated, they can be then reused for other types of tuning of neural networks. So it's just another way to highlight that if you have this imagery that is identifying trash, and you've done the work to annotate it, that those annotated images can be reused in different ways that may be helpful to someone else's efforts to kind of like detect something else. So, or in new ways, or perform further analysis. So I just want to point out these things, that sometimes you have to be careful about what you're detecting, but then also a lot of the work goes into collecting the images and having ground truth data that are paired to those images, and that shouldn't go to waste, and there are ways to repurpose them if you wish.
Yeah, definitely agree. I think that the value of the imagery, I think that's something that we're, especially trash imagery. I know, actually, I guess on a related note, I'm doing, that I'm working with Win through Code for America. So one of the projects that he's pitching for us is having a data portal for trash data and potentially imagery, and also a lot of these other, like, these apps that are collecting the imagery. Yeah, the annotation or just the raw imagery is really valuable. Yes, WinCoder. So we are working together on, and actually the demo that you're going to see today is actually kind of related. It basically is our current project for that. So we're partnering up with, both Win and then through Code for America. We're also having student volunteers and actually, maybe if I could indulge me for a moment here, but we are actually on GitHub. So this is the actual GitHub repo. It's public. And if you all are interested, we're starting to work on, we don't have much here yet. We're trying to work on a front end, but we'd like to take this model, which I'm going to share with you all. This is the project that we have for everybody today. But basically we'd like this to be the back end, and we're having student volunteers come in to actually help us develop a front end. So again, if you're interested in following along, we're going to be developing this, not just out of for fun of this event, but also this is a part of a larger project through Code for America. This is a Sacramento Brigade, which I'm a part of, and then concurrently also with WinCoder, we are working on what do you say that word? Spectrography. Okay, I'm just gonna call it that. So it's basically looking at water quality. We like to use machine learning, but the similar process of, he's got a tool that he's built. We'd like to improve it beyond just statistical analysis or machine learning. So again, we're trying to apply these things while using, benefiting the community, having students come in to work on projects, and then also making these tools publicly available. So both for trash AI. And so the goal is to have a photo upload with an image labeled with trash, for everybody to use. And then the other one having a spectrography signal be uploaded and then come back with a rating to be able to identify what is the object in this drinking water. But these two projects are going concurrently as we speak. So anyway, just wanted to throw that out there as well.
That's awesome.
Yeah, let me put this link in the chat. So I guess that's why you see me running around, Tony, when I'm doing these views. I'm like panicking. I'm like, oh, I got a lot going on. All right, so we're gonna go back to the slides here. All right, so I know I'm throwing a lot at you guys, but wanted to kind of, point out resources and different initiatives and projects that we have and ways to get involved. And also I would add to that too, within the organization, especially with Python, a lot of GIS developers, because of ArcPy and using Python for scripting, actually know Python. So if you're in an organization and you want to get started, I would say seek out GIS developers or those even analysts. A lot of what we find, because we're pretty large, right? But a lot of data analysts or folks in this space that actually just work with data in general have picked up Python along the way. Even like in Tableau, we started working with TabPy, which is a bridge in Tableau. You can actually do, instead of using Tableau Prep, you can actually use Python. So there's a lot of these tools now, like in Esri, you can actually just embed Python into in ArcPro. ArcPro now comes with Jupyter Notebook, so you can just write, Jupyter right in your application and then have it integrate. So I would say those are good entry points. If you don't know how to code, I say in your organization, look for data analysts, people that work with data, and then also GIS, because those will be places where once they know Python, you can kind of start to learn your way around. As you'll see, like the example that we have is basically provided by the TensorFlow Google team. So as long as you can kind of navigate, you don't have to completely write everything from scratch. And that's the benefit of some of this stuff. I'd say half of it is, once you understand the general concept, is then being able to source good examples, like finding things that are canonical from Google. And then once you can wrap your head around it, then start to do a little bit of work and customize what you need. And that's, I think, one of the hopes in the demo that we have today, which I will show now. So here is and I'm going to share this link in the chat, see if, let's see here. Let's see if this link works. Sorry, let me just give you guys a fresh link here. All right, so this is for edit. And I will say it'll require a Google account if you want to actually copy it. And I think to run it as well, but you're free through, if you just want it, it's a read only. If you don't have an account, that's fine. You can still go through and look at it, go through the actual text in the code. So what I'll do, and again, if you want to get hands-on, I would say you can copy. So thing to note is I already have this booted up. So if you load it up from your Google account and you're logged in, I already have a copy, but you can save a copy to your Google Drive. It is yours to keep, yours to take home, manipulate, break, re-break. All you have to do is come back to the link. I would say though, actually, because it's on edit mode, that I do have a backup. Maybe that's, well, I guess that's an interesting one. If we're gonna work on it, well, let's just see what happens. I guess try to go light on it because everyone's gonna have the same copy, but cat's out the bag, so to speak. So anyway, you all are now able to edit it. Yeah.
Do you want to just ask that people make a copy and drive if they have a Google account?
Yeah, sorry about that. Yeah, go ahead and make a copy first. Don't edit on a live copy. Yeah, probably overshared there, but yeah, just go ahead and make a copy. So if you see it, just do the save a copy. It'll show up. It should show up in a folder called Google Colab so the way it'll show up is you'll see that it should create a Google Colab. Otherwise, it'll just show up at the very top level of your Google Drive. It shouldn't be hard to find. So go ahead and save a copy. And if you know how to use GitHub, it'll actually integrate with GitHub for you. So nice little integrations along the way. General navigation, this is running Jupyter Notebook in the back end. However, it's a Google tool and it's a very nice thing to be able to, the interface looks like Google Docs, which is a very nice thing. Give me a second here. So All right, so continuing onwards here. So the look and feel of it is just like Google Docs, right? You can save it to Google Drive. You're kind of like it's organized in cells. So in this case, it's a mix of text and code. So in this case, this is just a kind of a preamble of what we talked about this morning. So nothing too much to worry about here. This is more just specific to the project. Some use cases. So again, I think we've gone over quite a lot, but one of that I thought was really interesting is Keep America Beautiful did quite an extensive study using TensorFlow, which is the tool in our example here. But they actually did quite an extensive study, and I'm going to put this link in the chat, but they actually did a full-blown schedule, and they did it on city streets, and they actually have, some pretty fancy visualizations and outputs. And then they were actually getting very similar scores. And this was done, I believe, on the East Coast in New York and done with about 3,000 images. And then again, for transparency, all of the code is available, basically. So it's been open source. So again, some different examples out there of what people are doing. And there's a lot of projects like this on GitHub. Again, I think the caveat is knowing what you're looking for, right? Really looking for the real gems of projects and looking for things that look like they may be useful. So that's kind of the preamble there. And then we talked about workflow, right? Field data collection, training the images, and then being able to deploy crews and do monitoring. Again, I'll note that we did not write this code. This was modified using a object detection template from the TensorFlow team. So yeah, you'll see that it's copyrighted by the TensorFlow team. And then they kind of embed some instructions here, but I'm just going to walk through the code very quickly. I know that not everyone may want to, you can code if you'd like, but basically here's all the setup and libraries that you need. Again, the nice thing is that this is done for you. If you want to cut to the chase and you have your own copy, the navigation here is like I talked about, right? You can save all that good stuff. You can even, if you want to download a copy of this entire notebook, you just go to the bottom, you can download a notebook anytime you'd like. And then obviously it's cloud-based, so it's just going to save as you go. Also in the UI, because it's basically connecting to a runtime on the back end, it's actually going to tell you that in this case, it looks like I have to reconnect because I haven't been using it for a while. This all runs Google Cloud in the background, along with Google AI. So you're kind of getting all this for free. Other stuff, probably pretty similar. And like I said, everything's organized by cells. You're gonna you can also like kind of add your text and code cells here. Runtime, if you want to cut to the chase, you can actually run everything all at one time and actually see what the output is, and it's actually set up to do that, and you can see that example. Spoiler is basically what it does is it takes an image and then it basically trains it, and using the AI model will actually give you some scores and some bounding boxes back. So that's what it's doing, and I'll show you all how you can edit it and work with it on your own. So again, they're kind of getting more into the kind of the nitty gritty here of, they're going to start loading up, the libraries and dependencies. This stuff helps. And so what they do here is there's a wide variety of models that are available. And I'm trying to see if there's a UI available. But you'll see that there's a full list here. A lot of these are the names of the models that are available, and these are generalized models. So things like Hourglass, ResNet, again, they just go by fancy names, MobileNet, ResNet. So these are different models that, and for different resolutions, and they're all on the TensorFlow Hub, which is a place to actually, let's take a look here. Let's take a look at TensorFlow Hub. Sorry, let me grab a link here from the chat here. So if we were to go just to one of these examples, I'll show you all. It should get to the Hub portal. So yeah, so here's basically where you can actually get to a whole collection, and it's actually taking, so it's been trained on the COCO data set. So like remember, this is the full taxonomy of photos. And then they have actually developed a full set of models, which according to this code, you can just basically drop it in, and they actually create a little UI for you to select from these, which we should be able to see down below. But it'll actually populate with these different options, and I'll show you guys how you can run it with different models and different settings. But just for transparency, they published everything. and you can actually see now every model. They actually tell you, what it's trained on, what what type of model it is, and then you can actually click on each one of these and get the details on each one. So it's basically a repository of models, open source by the TensorFlow team, which is basically industrial grade stuff. A lot of this stuff powers like Google Images and all the stuff in the background that you see in their app. So pretty powerful stuff now available for public use. So put this link in the chat so you all know that what is actually powering the models behind the scenes. Continuing onwards here. So there's all 39 of them. The one part here is, I'm trying to figure out if I can expand this because it's kind of annoying. So that they actually preload some images for us, but what I did was, and I'll show you guys in the code. Basically, they give you some stock photos to run as examples, but I went ahead and swapped out the image. I'll show you guys where to do that, and then that way you can take basically your images. I'll show you guys also if you go to Wiki Commons, that tends to be a good place for images, and then you can just drop those in. The one thing is, it has to be able to you have to be able to web scrape it. In a way that it'll actually accept. So you can't just throw in a web page. You actually have to give it an image that's linked. So I'll show you guys how to do that in a moment. Visualization tools, so you don't have to worry about, they'll actually help you do the actual bounding boxes and actually render them. This is stuff that's setting up on the server. Again, all this is kind of done for you. When you automatically run, it'll just run through all these cells. In this case, they're actually doing labeling of the image, a little bit more set up there. This is where we get to the selection of the model. So you don't have to worry about coding. You can just select the model that you want. So again, different models that run at different resolutions and different speeds. If you want to do your research on what they're doing, I would say, again, click on the TensorFlow hub here, right? And you can learn more about it. If you type in any of these names like CenterNet, ResNet, you can probably learn more than you want to know. You can go all the way back to academic research. A lot of these are vetted. They've been, over a decade in the making for some of these in development. So plenty of info on each one of them. And then in this case, we're going to load an image. So in this case, this is where I did the change. So if you want to import your own image, I did it here. So in this line where it says load image, I actually then imported an image from London, England, and this is from Wikimedia. And down below, you see it. You don't see the beach. So the way you do it is I kind of sidestep this little toggler, and I input my own little URL. And then I actually get, voila, the trash image with not annotated, just the raw image. This is the output. So if you all want to pick your own, image, you can actually go and search here. And what I did was I did a search for trash. So if you want to do that, these images are going to be, and I'll show you guys how to do that real quick. So if you want to, I pick a trash image litter. So the way you do that is, you would pick one of these where it's like an item. So if I wanted to say I want to pick this one, the way you want this link you want to drop in is, let's pick this image first. So you actually click on the image, and then what you do is you say use this file, and then you actually get the link. You actually want this link, and then this is what you would drop in. But this is how you take that link, like say I want to update my image, I would basically just take this, copy it, go back to the actual notebook. And then in the code itself, I just have to replace this one line. Don't have to worry about the other stuff. Just click on the cell and then import it. And then there you go. And I'm going to put the Wikimedia on here. I just want to highlight this because it's actually quite difficult. It took me a little while to actually find images that are strictly linked. Usually, you need to host it somewhere, so on and so forth. And then also the copyright and all that stuff. So this is kind of one way to go about it. So Wikimedia, so if you want to upload your own image, and then also remember, pick your own model, you can customize your little classifier, if you will, and put to work what we talked about today so far. So continuing onwards, this is a raw upload image. I believe on the scales here, these are the number of pixels. This is quite a large image, as you could tell. And then here's where they actually do the analysis. So they actually are going to help do the detection bounding boxes. And then they'll actually do the classification. And then in this case, it's actually going to run. So you can see that it actually did the bounding box. And I believe it gave back the score too. Some work to do here is we have to scale the image because we can't see what this is, unfortunately. But, you know, again, just proof of concept that, yeah, I think he gave back the scores of what it is. But again, at least if you run it, maybe if you feed it a smaller image, you know, from Wikimedia, you might be able to, you know, you'll be able to see the labels. And then again, a little bit more.
How is there still coffee in that?
What's that?
That's impressive.
Yeah. You mean the labeling? Like,
no, just the coffee is still intact inside the cup.
Oh yeah, yeah. Someone just left it there. It looks like it's a sidewalk. Yep.
Yeah, no, I think, but to your point about scale, that's something that we found to be also, it can be confusing to the detecting algorithms. If you are up super close, you know, if things are huge or there's not enough orienting information around it, then it's unable to detect it as an object that it recognizes.
Sure. So yeah, this is kind of the part about. So this is computer vision part. I'll pause for any questions or comments because I have one more demo to show you guys. Basically, to complete that workflow I was telling you guys about, right? The computer vision part of it, and then the tabular part of it, or how to classify your data. Feel free to chime in. If not, I'll go ahead with the second demo. So again, feel free to experiment with this. Yeah, just make a copy, experiment with dropping your own image, changing the model, and then seeing what you get. And I would say we found that it was so-so. I mean, we played around with it a little bit. We have a lot to work, a lot of customization to do. It's going to be good for generalized objects. So if you put, yeah, like a dog or a cat in here, it's probably going to do fine. But if you put like trash and litter and a bunch of stuff in an image, it's probably going to struggle a little bit. But I just want to give a heads up. But you know, this is obviously just to get everybody kind of exposed using a Jupyter notebook. Everything is kind of prepped for you. And then again, you can have your own copy to keep. So that said, let me go back to the slides real quick. So here's the other, and again, I will drop the link in the chat. Let me see if I have the slides here. Do you have the link to the slides, Tony, that you could drop in the chat?
Yeah, absolutely.
Oh, yeah, that way everybody can, yeah, feel free to make a copy of the slides or at least reference the links there. And then that way, again, you have a link to all the resources. So we're going to take a look at this classifier real quick. You know, this is using City of LA street data. And then this is a way of, you know, basically doing, you know, classification on actual trash data. And then before we do that, let me also point out the other resources that we have. So R is not, or Python is not the only way to do machine learning. There's also R. So R is a statistical programming language. There's a framework called Carrot, which helps you do machine learning. So for those that want to program in R, it's available. So the link is there. And then also open data or data visualization, like I talked about. So this is using generating maps using Python. So it kind of fuses where, you know, you can do some machine learning, you can do some visualization. And then again, there's tools to do mapping and analysis that way as well. And then also some open data sets, right? We want to be able to have you know, data sets where, you know, again, for litter data or just in general, but this is kind of the larger ecosystem when we get into data science, right? Not just in litter, but just getting access to good data, like Tony said, you know, the value of some of these images. And then also, like I've mentioned, you know, some of these tools, and these are using Google Colab, but being able to share your results, being able to visualize things, present them effectively. These are kind of all in a larger realm of data science that apply to this in particular for litter detection. So with that, let me go ahead and open up this notebook. So this example is from earlier this year when Tony and I partnered up again. And so this one it uses the City of LA CleanStat data set. Let me show that off so that'll load up. But basically, same format, right? We're using the same tools, code and text. And in this case, this is just kind of a setup. This is not the actual code itself. This is just for working within Colab. And in this case, you know, they're trying to show, you know, ways to plot data, right? Just very basic stuff in Python. And then we're actually going to move into now the machine learning and the actual consuming the data. So this is the example that we had, or I came up with last year. So in this case, I actually did roll the code. You can completely write from scratch. So this, I just brought in some machine learning and start to actually pull in the data. So this data is pulled in from CleanStack. In this case, let's see the overview here. So this is the actual data set itself. And then this is using trash level data based on their assessments in the city of LA. Let's see if we can zoom in and see some categories here, some labels. I guess not, kind of bummed out, but anyway, that's where we pulled in is an actual CSV file. And we actually start to do some analysis and some subsetting of the data. And then this part just breaks it up for the machine learning part so that we can actually train on the data. So we're going to feed it the data set and then pick out one that we're actually going to try to predict. And in this case, this is the actual trash level. So in this case, just getting a preview of the data. This is the contents, about 30,000 rows. They do their labeling based on the types of trash. And then also they try to arrive at a score. So the segment score is the one that's going to be the prediction. So that's going to be a value. And then in this case, continuing onwards, subsetting data a little bit. So we can see that we want to basically, subset the data and then set aside the training and test. So in this case, we set aside, I believe it was like a 80-20 split or 70-30. So we have about 30,000 and 7,000 left over for the test. Set ourselves up for and getting an example, these are the columns of data. So in this case, trying to keep it simple, we're going to take the trash levels or the scores for these particular items and the ID number, and then just trying to take a smaller subset of the data and then also splitting it for the training and test. And getting a look just for some visualization, so just for some data discovery, getting a look at what this data looks like. So in this case, this is just the segment score, trying to look at the distribution. So we can see that at least in a kind of the grid within inner city LA, obviously, 0 to 3, 3 being the higher. There's going to be some that are in the higher category, but a lot kind of in the, you could think of this as like the low to moderate, a lot of stuff in the middle here. And sorry, let me also give you a copy of this note. Well, you have it in the slides, but if you want to follow along, here's the notebook as well. If you want to follow along with this notebook, same drill. Remember, just do a save as, and then you can have your own copy. And then a correlation heat map. So we actually want to see what this data set's doing as far as in relation to each other. I think Tony, you pointed out the correlation. I addressed that. So we took out the funny little, like, I think it was the red boxes. So I looked into that. So it's just masking it a little bit, but not a whole lot of correlation. If anything, some negative. So, the segment score, it's kind of hit or miss, with some of these others. So I guess in a way, because these other scores contribute to segment score, it's just because they're related. It's not necessarily they're correlated, right? It's like one, these scores, these individual scores make up the total. So that's kind of their relationship. Random, so this is the random forest, right? We talked about classifying. So remember, like we talked about for our model, right? We're going to take some tabular data. In this case, that's essentially what this is. It's a GIS layer, but it's got scores and it's got locations, kind of like the way we did highways, right? Segments and then scores. And so once we get back the computer vision part of it, take the scores and then feed it into the second model. So that's this is the example of the second model, if you will. So the random forest, and then we're going to feed it, give it some parameters as far as just how many times to run, what's the technique it's going to use. But basically, this is the scikit-learn model that we use for random forest. And cutting to the chase here, we first train it and then we actually test it. And so the output here would then be, again, similar to the way we did computer vision, but they actually do the confusion matrix, and we can see that relatively it did well. It seemed to fit well. We want the scores to be in the middle, the predicted versus the actual scores. Though we'll notice that, yeah, there were some false positives here on the lower rankings. But overall, in general, it tended to score pretty well. And I think that's it for this one. This is really kind of what we're looking for. We want to be able to make some predictions And if you want, there's some other settings too, where you can actually then, the results are actually in, I believe, this data frame. So once you do that, this is actually just for the confusion matrix. But if you actually want the scores, you can actually just download it as its own data frame. You can take the Python data frame and then download it as a CSV. So you import the data, run your model, train test, and then you export it, and it would give you back the CSV file. So that would be the workflow. So any questions or comments?
I have a question. So how many of you have used these collab notebooks before? That was a test to see if Lorenzo was listening. So yeah, that's cool. Thanks, Lorenzo. Okay, so a lot of these are new to you. So again, if you could just like clap or make some kind of response, maybe do the green or the green checkbox. How many of you might be interested in digging into these things a little bit more, exploring them, or in fact sharing them with others who may have skills to work with them? A number of you. Okay, good. So that's great to hear. Whether you're using them yourself or you're trying to encourage your colleagues to use them. Just just to emphasize what Walter said about their approachability. You don't have to set up a really complex environment or provision server space or have any of that expertise. It's really approachable. So when people are like, oh, I don't have time to kind of set all that up, it doesn't take any setup. So it makes it really, really straightforward to work with.
Yeah, and I got to run to at 3 o'clock. However, I will leave my contact in the chat, so feel free to reach out to me as you're working along. As I mentioned, I work. I've taught these at CalTrans to almost begin, very, very entry level. Like people that are from scratch. So happy to continue to share resources and best practices as you're learning. So yeah, no worries at all. I know it's a lot to take on at the beginning and kind of threw the fire hose out there, but I only had day one here as I'm kind of trying to save our litter abatement. So I've been pretty busy with Clean California. So only make today, but put the email in the chat. Yeah, feel free to reach out and happy to compare notes. And with
Thank you very much, Walter.
Yeah,
it was great. It was great to share this time with you, and we really appreciate all of your expertise.
Yeah, you're welcome. And sorry, it was a little bit rushed, but got it all in there in time. And again, the slide deck and all the links are in the chat. So, and with that, I'm gonna sign off. But thank everybody for your time and thanks for participating.
Thank you, Walter. Well, everybody, you hang in there for just a sec. We can wrap some things up. So thank you very much. So while we're still here, let me go ahead and share my screen real quick. Just wanted to see if you all had any questions about or observations about today's discussion, whether in the morning or in the afternoon, or how the Google work might sync up and complement some of the things we've been talking about in this work group. Just figure that maybe we can use this as an opportunity for a free-form discussion if you'd like to ask questions of each other. Even I don't have to be I'm not the arbiter of this stuff.
I'm curious how many other groups are collecting litter data and using machine learning to study it.
Well, I welcome others to chime in. So Bob, you've talked about your efforts to encourage the use of artificial intelligence and collecting different or using information that's already collected. And we know that there's Fusco Environmental is out there doing their thing. Second Nature, Google, of course. It seems that people are seeing the opportunity as irresistible to leverage these technologies to get deeper insights in ways that are very difficult otherwise. Bob, did you want to chime in?
I would just comment that prior to my involvement in sustainable materials management and water work, I worked with a lot of mainstream manufacturing companies, and all of these things that we're just now seeing come into our industry have been tried and tested there. And it always frustrated me that everybody's using it up to the point of consumer purchasing. And then once that item is purchased, everybody just drops it and doesn't care what happens after that. So I've been an advocate, and I'm happy to see a lot of other people are, for bringing all these tools and techniques into our field to try to create a better environment and get back to where we need to be. And also some of my clients are even tying it back into circular economy and jobs and everything else. So it's great to see. And right now we're collecting data from approximately 40 cities in Southern California using SRE as many others are, and then doing a lot of our own analytics on top of that. And we hope to gain some great insights, and we hope that our partners there will allow us to share everything possible with the public so we can all learn from it.
Yeah,
Fantastic.
just to dovetail on what Bob just said, this is Zane Harvey, CTO Mobius. I'm in a camp, so it's a little bit hard, but we are doing lots of litter surveys and lots of litter collection of both quantitative data and images. We've been doing analytics on the quantitative data and are starting to look at classification and things like that of the actual images that are collected. So anyone out there, please feel free to reach out to us, and we'd love to discuss.
Thank you so much, Zane. Sorry we didn't invite you to introduce yourself more properly earlier.
Oh no, yeah, I'm working with Bob. I'm the CTO of Mobius, and we're doing lots of great work and lots of stuff related to what we're talking about here today. So please feel free to reach out to us, and I'm sure we'll be seeing everybody in the future.
That's great. Yeah, as much as possible, we would like to facilitate more collaboration on this. While there are a number of people, kind of making a go at creating these algorithms and tuning algorithms that are out there and doing transfer learning, there are an equal number of people kind of like recreating, reinventing the wheel, as it were, doing their own individual collections, some of which might benefit from leveraging across different geographies, or leveraging the work that others have done before them. So it's a great question, Alina, and I think that Literati has done some fantastic work to leverage these technologies, and it's interesting to see a number of others who are kind of coming up to speed on it as well.
We're also doing lid flips. I just wanted to say an application that we're looking at now is we have people out in the field doing lid flips as required by SB 1383, actually walking around neighborhoods and flipping bins and seeing if certain bins are contaminated with things they shouldn't be, and then taking a picture if so. And we're looking to use this type of technology to kind of automate that process. Right now, they're just eyeballing it.
Yeah, so we, I'm trying to remember who talked about smart bins. I don't think she's here, but it was Denise was talking about the application of smart bins in commercial buildings. And so if I'm understanding you correctly, Zane, you're talking about employing some devices in bins.
Eventually, yeah. I mean, right now we're just relying on the people walking around in the field in operations, taking pictures, with their camera, but that could be a potential. Yes.
Yeah. Well, that's great. Bob, did you want to add something to that?
I just want to comment that I know there's one group, it's not us, but they were doing using an AI model to analyze contamination rates by somehow scanning bins. And I'm not sure what they're using, what technology, That's not us. And I am aware of the big bellies and other bins that we're trying to detect, have detectors inside the bins that have come with mixed results. So right now we're just using vision, and we're using human eye and capturing photos. And we'd love to take advantage of any of the libraries that are out there to help train models and then take it to the next level so that we can automate a lot of this and collect more data more efficiently. And then any of the cities or publicly funded projects we're working on hopefully will allow us to share all that data also to contribute to the larger data pool for everybody else to use as well.
That's great. You will note that that Walter's links are in the chat. I encourage you to grab those. I will be sure to note them down, and I can share them. I can reshare them.
I've grabbed them, copied them, bookmarked them, and shared them with Zane for discussion on Saturday. Thank you so much.
Yeah, because the presentation, if you get nothing else, the presentation is a good jumping off point. So if you have that presentation, it has a lot of links embedded in it. So you can come back. I'm flipping through it here, returning to this, kind of family tree of artificial intelligence. It was really cool to have, I thought it was really cool to have Walter step through the history of artificial intelligence. It was something that I encouraged us to review because I think getting oriented not only of the current status of these different categories of artificial intelligence, but also, kind of where this came from and when things happened, because some things are really, really old that have only just been renewed recently, but it's interesting to know when things came about. I wonder if people are at all, I can understand fully that you might be completely confused by some of what we've been talking about, whether it's natural language processing or this distinction of computer vision versus some of the data visualization that Walter was reviewing. Do you have any questions about any of those kind of categories of AI? One reason why it's important, the reason why I asked the question is just because as you are working with technologists, or you are a technologist, collaborating with others, it is important to know kind of if you are in the right realm of work. And so understanding the difference between the random forest and convolutional neural networks and things like this as tools to get you where you need to go is a good first step along the way. Maybe actually, we have about 5 minutes, but Lorenzo, if you're still there, you had your initial exposure to AI was, as I recall, through the use of random forest in some gene mapping, but maybe you can talk about kind of what it was like to make the transition from random forest into neural networks.
Yeah, no problem. I think especially when we're talking about random forest, one of the challenges, and even for my graduate work, and just so everybody's aware, like, so I graduated from San Francisco State University back in 2014. My master's thesis was about bringing in an additional algorithm into an existing software data pipeline for doing protein functionality prediction. And so with random forest in particular, we wanted to compare it to the existing machine learning algorithm that was already implemented in the system, which we were using support vector machines, which you'll see, I think I saw it referenced in some of the materials that were shown today. And one of the challenges that came up was for random forest, there's actually a scoring that comes out called the out of bag error, which you can leverage to identify how well your random forest model is performing. Now, if you want to compare that to another machine learning algorithm, such as support vector machines, or even a neural network, you can't, it's not an apples to apples comparison. And so you kind of have to modify your machine learning experiments in order to properly compare and validate against other models. And so that was one thing that, when it comes to neural networks, it was important to sort of like be able to validate how well the model was performing. And so I had to use a more traditional sort of like a confusion matrix, finding my true positives, false positives, coming up with average precisions and recalls, which, you know, when I was doing my random forest work, it was a lot more of the out of bag and variable importance. And so it was in the nuance of the actual classifier. I think sort of the next step, and to answer your question more thoroughly, with neural networks, you know, there's a lot of parameters that you can tune as part of that process, and those were very foreign to me. So I had to really do a lot of research into the models that I was using, because I wanted to make sure that we were trying to optimize for some of those parameters as we conducted our experiments, and that required sort of within the TensorFlow realm, this like pipeline file with all of these different parameters, hyperparameters, if you will, and you can basically set them and then run some experiments. But you know, that's time consuming, it costs resources, so you have to be very tactical with what you're doing. I think that you know, the space has come a long way to where a lot of the tools that that were introduced today, that that a lot of them kind of do that under the hood, or they're using sort of like defaults, or they're using, and I don't know the details for a lot of the newly implemented tools that sort of take you out, like give some rails, but it seems like there's a lot of best practices that have been integrated, so you have to worry about that as much as we did when we started our work. So yeah, I think those are the main things. Is just you know, the model details and how that translates to parameters. But you know, for the most part, in a lot of these frameworks, they really do let you swap out the heart of what the analyses you're doing. And I think that's really powerful and important. And I think one of the spaces here one of the things here that I'd like to see more is comparison of different types of classification tools. It's hard to say what, because, you know, neural networks, specifically convolutional neural networks, are so, you know, historically good at these image classification problems and segmentation problems that, you know, I'm not familiar enough with the current research just to say what a good alternative might be, but I'm sure that there's other workflows that people can leverage.
Yeah, and ensemble modeling as well. Lorenzo, have you gotten into ensemble modeling and combining these?
You know, we had to. So my part of this project right now is sort of on pause. We're hoping for more funding, but that's certainly one of the avenues that would be really nice to go down, is an ensemble method where we can leverage multiple models and maybe even like weight their scores. You know, that certainly feels like a lot more powerful,
right, for
this application.
And like you said, they all have their own hyperparameters that need adjusted, so you have to learn each model. But yeah, I think what Lorenzo said was spot on, and he did mention data pipelines, something that I think is somewhat missing. Well, maybe it's not missing, at least from the discussion, but from this slide is the data engineering, which is what we do a lot of, actually building the data pipelines and the data flows so that we can actually analyze the data, you know, get it from one system to another, and make sure it's, you know, all the systems are updated and in sync, and then being able to do the actual modeling. So we do a lot of the data engineering. I'm going to post a talk I'm giving on December 1st. It's a free workshop online. Please check it out. Thanks, everybody.
Yeah, thanks, Ang. Well, it looks like we're being called back to the main room. So rather than push it to the very limit, we might as well leave this room and go back, and I'll see you in the main room. Okay, bye.
Thank you. Bye.